not go? Either one. But yeah, we will get a chance to see everything there. Okay. So, next, well, it's actually two sections. I combined them together because they're relatively short, okay? 2.1 and 2.2, it's the rectangular coordinate system, which you've done all through your math career. It's plotting points and different things like that. I'm not really going to focus on that part of it. Look. Hey. Okay, in the middle of recording right now. Yeah. Okay. All right. Thanks. Bye. I hate the phone. Hate the phone. Okay. So anyway, and then the last part of it is circles. So circles is the 2.2 section. But our objectives: this is a midpoint formula. Identify x and y intercepts. Write the equation of a circle in standard form, and then write the general form for a equation of a circle. Okay, so that's what we're tackling. Cool. But first, a little history. We don't get enough chance to really talk about history, Mass. So let's throw some historical notes in there. Let's talk about René Descartes. We talked about him already. He helped us with some complex numbers. He made some contributions with that. But this is the guy who was the first to identify points on a coordinate grid by a pair of coordinates. Okay. He also created the coordinate grid by intersecting two perpendicular lines in which form the rectangular coordinate system. Okay, so a couple things. So he was the first to identify points on a coordinate grid by a pair of coordinates. He created the coordinate grid by intersecting two perpendicular lines, which form the rectangular coordinate system. And the rectangular coordinate system is also known as the Cartesian, that's fancy, coordinate system, named in René Descartes' honor, which is kind of sweet, huh? I mean, he came up with the rectangular coordinate system, so it is sometimes called the Cartesian coordinate system. Cartesian is the, if I believe it was the Latinized form of his last name. Okay, bless you. So they Latinized his name and called it the Cartesian coordinate system. So yeah, he's the one to blame for all that stuff that you went through for how many years? I shouldn't say it like that. It's actually pretty cool. Okay, let's talk about distance work. So given our Cartesian coordinate system, okay, and let's say that I want to find the distance between any 2 points in a 2D coordinate system, okay? 3D kind of follows the same pattern, but 2D just with x's and y's. So to figure this out, we got to start taking into consideration the distances that we traveled in the x coordinate direction, right? And the distances that we traveled in the y coordinate direction. So this way, this horizontal way, will be the difference between the x's. Okay? And we use the absolute value because, again, I don't care if it's negative or positive, I just want the actual number. How far did I travel from this point to, well, the x coordinate for this point? And then do the same thing, how far did I travel vertically in the y directions? So that's me subtracting the y coordinates, okay? The subscripts, if you remember, that just tells you what point you're looking at. So this is the second coordinate point for the x's, and this is the first point for the x coordinate. Same thing for the y's, okay? So I create a nice little right triangle with that, and if I want to find the distance, like is there a way to formatically like compute it, we can use Pythagorean theorem, right? A squared b squared equals c squared. So hey, not only do we have René Descartes in this, but we also have Pythagoras. He jumps in too. Okay, so Pythagorean theorem. So we have our distances for the x's and y's. Okay, we're going to square them, and it's equal to the hypotenuse, which is our distance squared. Now, one thing to note, I did jump a little bit here. This is the same thing as this. Okay, they're equivalent to each other, and you'll see that a lot in future math courses as well, where we actually substitute some of this information. Now, one of your homework problems, I forget which one it was, you had to come up with why are these the same, right? And it's because they give you the same answers. If you're squaring this guy, you're always going to get a positive, right? Well, absolute value is always going to give you a positive, so these are equivalent. So instead of me writing both of these here, I just plug in their equivalents. So to solve for d, our last step is to take the square root. Typically, we, when doing the square root of anything, we include a positive and negative term, but I don't need to do that here because we're talking about distance. So we're just doing the positive end of the square root. Try an example. So find the distance between the points -7, 11, and 1, 5. They want us to give the exact distance and approximate to 2 decimal places. Okay? So give the exact distance, which means if it's a square root that doesn't break down, leave it like that. And afterwards, plug in the calculator and see what you get. Okay? All right. If you'd like, do I got colors? I got colors. I got pink. We'll use pink. You can label things. Doesn't matter what your first or second point is, because if you think about it, the exponent here is going to get rid of any negatives, so that's why the order doesn't matter. We can let that be the first one, and this be the second point. So x1, y1, x2, y2. All right, and we just plug them in to the substitution step. So we're going to subtract the x coordinates. That's going to be 1 minus a -7 squared. Always be careful, we have subtracting a negative, so that's going to change to a positive. And then we have 5 minus 11 squared. Now, we said that's going to turn positive, so that's 8. And then we're going to square it, that gives me 64. I'm going to do both steps in my head there. That way we don't have to fully rewrite everything multiple times. And then over here we get, it'd be a, I'm blanking out, 6, sorry. It'd be 6 squared would be a 36. There we go. So for this guy, 64 and 36, that would give me 100, right? And square root of 100, 10. So we didn't have to worry about the 2 decimal places in this case. It actually did break down nicely. Okay. Bringing back memories from geometry. Just a little bit.
They're actually learning that right now. I was in there.
Really?
Yeah.
How about that? kick it up a notch. Determine if the points 1, 8, 1, 5, and 3, 7 form the vertices of a right triangle. Okay? So those 3 points, they make a right triangle. One thing you don't want to do is just plot them on a coordinate grid and say, looks 90, we're good. If engineers did that, I wouldn't be driving on bridges with them, that's for darn sure. So what I would do though, I would just draw a quick picture. That's gonna help us set things up. So let's see, I'm gonna go 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So 1, 8 is here. 1, 5, 2, 3, 4, 5 is here. And 3, 7 would be right there. There we go. Okay. So there's my triangle. Now again, doesn't quite look like a right triangle, but don't go based off of looks. Let's actually prove it algebraically. So what I do know is this, okay? If it is a right triangle, then Pythagorean theorem is gonna work, right? Okay, we call that, if you remember from geometry, it was the converse of the theorem. Pythagorean theorem is, use a theorem if it's a right triangle. The converse is, use a theorem to prove it's a right triangle. Okay, you're going the opposite direction with that theorem. So let's do that. Let's call this distance 1. We'll do this as distance 2, and this is distance 3. That way it's a little bit easier that way, okay? So let's see, distance 1 is the easiest. It's a vertical line, so just subtract the y coordinates. So that, and I probably, well, tell you what, let's write these over here. So this is 1, 8, 1, 5, yeah, 1, 5, and that's 3, 7. Okay. The picture's looking even goofier now, isn't it? There's a lot of stuff happening there. So we have 8 minus the 5, so that gives me a distance of 3. That was nice. Again, the opposite value's in there because I don't care if it's negative, I just want to know how far you traveled. Okay, the second distance, well, that's at an angle, right? So I'm gonna have to use distance ruler to figure out the full length of it. So that's gonna be D1 and D2's points. Okay, I'm gonna have to use those. So I get 3 minus 1 squared, and then 7 minus 8 squared. Okay, so this will give me a 2, squaring it gives me 4, that gives me a 1, squaring it gives me a 1, so that's just square root of 5. And then for distance 3, okay, so that's gonna be 1, 8, and a 3, 7. So you can kind of see why you want to draw the picture. You can be able to keep the points in the correct orders there. Just makes it a little easier. Okay, so in this case we can do 3 minus 1 for the x's, and then 7 minus 8 for the y's. And again, order doesn't matter. You could have flipped these. The exponent takes care of the negative, so it's all gonna work out. So this would be a 4. That's gonna be a 1 again. And hey, we get square root of 5, huh? Got that twice. So, now what do we do? Well, let's plug in the Pythagorean theorem, right? Let's see if it all works out. So is 3 squared, and you could probably see ahead of time, is that equal to square root of 5 squared and square root of 5 squared? So let me just stop there. What do you think?
No, you used 1, 8 twice.
Did I use something twice?
1, 8, like the point 1, 8.
I used 1, 8 twice.
So,
Oh, you're right. I did use it twice, didn't I? So that's gonna be, it's this guy here, huh? I wow. How did I miss that?
It seems like an isosceles triangle.
Wow. Let's change that. Thank you. I was thinking, I'm looking at my notes, and like, I don't remember square root of 5 coming up twice like that, but maybe I just don't remember. I did all these notes during the summer, so it has been a couple months. Okay, so let me change that then. So it should be, for this one,
Square root of 8, right?
Yeah.
should be square root of 8, yeah. So it's gonna be, I think I mixed these up. Hold on, let me see here. So this is the square root of 5 one, which is good. That's awesome. For this guy, it should be 3 minus 1, and then it should be 7 minus 5. That's better. So this is 4. Okay, this will be 4, which gives you square root of 8. Now we're on track. Okay, so this is square root of 8. And please, just like interrupt me. If something's not right, let me know. This is one of those things where I'm not used to having notes in my hand and keep going up and down with it, so there could be something I write down incorrectly. Now looking at this, that's a 9, that's an 8, that's a 5. Well, I don't think 9 is going to equal to 13, so therefore, it's not a right triangle. Now that's not the official way to write it, obviously, so let's actually put some math to it. So 3 symbols there, so that's therefore the 3 points do not form the vertices of a right triangle. All right. If it did work, hey, you got a right triangle. All right. So far, so good. Like I said, that should be kind of a review from geometry. So we did distance formula. I guess that means midpoint's next. Now think about midpoint for a moment. If I want to find the middle of a number, well, I shouldn't say a number, middle of a range of numbers, like what's between 10 and 20? Not your question, on 15, right? Okay, what's between 20 and 30? 25, right? Okay, now instinctively your brain just kind of knows that, right? You know what the middle is. But how can we get that algebraically? Well, just add the 2 numbers and take half, right? So between 10 and 20 is 15. So 10 plus 20 is 30. Take half, you get 15. I'm going to do the same thing for midpoint, except I have x's to do that to and y coordinates to do that to. All right? So let's look at the midpoint now. So the midpoint of the line segment with endpoints x1, y1, and x2, y2 is following. The other way to describe this formula is they call this the averages, which makes sense. If you take the average of 2 numbers, you add, divide by 2. So I don't know if you want to put that over here. It's the average of the x coordinates and y coordinates. That helps you to memorize that. It's not too bad of a formula to memorize, I will say. So an example. Find the midpoints of the line segment with endpoints of 1.2 and 4 and negative 2 and 3. Okay. Well, using the formula, and if you'd like, where'd that marker go? There it is. You could label things, but because we're adding, I don't think labeling's really necessary. You can just jump into it, but do what's comfortable to you. I don't want to force you to go one way or the next with it. So I just named this the first and second. Again, doesn't matter the order because we're adding, so we know that addition is commutative. So midpoint is going to be 1.2 plus negative 2. Then we'll take half. And then the y is 4 plus 3 over 2 and and take half. Right? So the first one's gonna give me a negative 0.4, and the other guy will give me a 3.5. Not too bad, right? So that was geometry. Let me ask you this. If I were to, and this isn't part of the notes, but just to throw it out there, if I were to expand this in 3 dimensions, now we got a z-axis, right? For the distance formula, what would I do to change it to include that extra axis, that extra dimension? What would I add to it if I have z coordinates? Yeah.
Oh boy. Would you have to do the formula for a pyramid? No. Right now.
Don't have to. So,
I thought I knew, and then I didn't.
that's okay. You just have z coordinates, right? So you just be adding z2 minus z1 squared.
Coord.
That's it. Mhm. You're still using Pythagorean theorem in a way with the 3-dimension stuff. Looks actually pretty cool, but yeah, that's all you're doing. So if I have a midpoint in 3 dimensions, then what? I would just not do this, I would extend it, right? And just go for all 3 of them. You know, what's the middle between all 3 dimensions? Okay, just something extra to throw out there. Make you think. Next, let's identify x and y intercepts. Let's do this formally. So definition. An x-intercept is a point, A0, where the graph intersects the x-axis. Okay? And by the way, A is just any number. I mean, they didn't put x in there. I know x is a common variable, but if you're saying x-intercept, it might not behoove you to put x there in its place. Y-intercept, same kind of definition here, just flipping it. So is a point 0b where the graph intersects the y-axis. Okay, so in this case, I use b for whatever that number is going to end up becoming. Okay, so again, just formal definitions of how you would write that in a math sense. Okay. I think what's interesting is your lower grade levels, they have their own way to define things, right? And there's nothing wrong with defining it that way. But as you learn more math vocabulary, you learn more symbols and notations, then you start upgrading those definitions a little bit more. Let's try an example. So let's find the x-intercepts and y-intercepts. Okay. Now the reason why the s is in parentheses, well, that's because it could be 1, could be more than 1, right? Just depends. So here's our equation. Okay, find the x and y intercepts of this guy. So here's what I would do. Can I just start, like as you see here, what, plug some zeros in and simplify? Yeah, there's nothing wrong with that. I think it's a little easier if you set one of the variables equal to the other one. So I'm going to solve for y first, and then start plugging zeros in. Okay? But again, you can do anything you'd like when it comes to simplifying. So I'm going to go ahead and subtract the 4 to the other side, and then take the square root. So that means it's a positive or negative square root of x plus 5. Okay? X-intercepts. So if you look at the x-intercept, if it hits the x-axis, that's when y is 0. So I'm just going to plug 0 in for y. So 0 is equal to the square root of x plus 5 But you also have another case here. 0 could equal to the negative square root of x plus 5. Okay, so we have two options to consider there. To get rid of the square root, square both sides. So we get 0 equals the x plus 5. Okay, so then x is equal to negative 5. It is a point. I wouldn't leave it like this because technically if I'm graphing it, that's a vertical line. So let's make it a point, so it'd be negative 5 and 0. Okay, on this side, I'll square both sides. Now that negative that was there is gone. So you can kind of see that I'm going to get the same answer. So there's really only one x-intercept I have to worry about. Okay? Which is nice. Let's try the y-intercept. That's when, if you look, that's when it hits the y-axis, which means the x has to be 0. So we're going to plug 0 in for x. So y is equal to, and again, we have two cases to consider. So the positive one, so it'll be 0 plus 5, or we can have y equals negative square root of 0 plus 5. Now, unlike the x-intercept, this will actually come out to two points. So this will just be y is equal to the square root of 5, and this is y equal to the negative square root of 5. Again, you want to write it as a coordinate pair, or else Descartes will come back from the grave and haunt you. You don't want that to happen. Math people in person are scary. Imagine them from beyond the dead. That'd be awful. Now, graphing it. Let me see if you remember something. Remember transformations, which we'll cover again. So, a plus 5, would that move the graph to the right or left?
Left.
It's going to move to the left, right? Do you remember how square roots, it's just that curve, right? Is what it is? Well, because you have a negative curve, you also have a curve up top and a curve underneath the x-axis. So as a visual, I already know what it kind of looks like, but the nice part is the intercepts are going to show me that as well. 1, 2, 3, 4, 5. So there's the x-intercept. The y-intercepts, well, square root of 5, so that's like 2 point something. So we'll just put a point here and here just to estimate, and then draw my graph. And there we go. Okay. Which is pretty good. But again, if just based off of what we did last year, if I were to cover that up, it went to the left 5. So finding the x-intercept, we actually proved it to go to the left 5. All right, that's the rectangular coordinate system. I'm gonna need more board space. I'm gonna go back to the first board instead of writing underneath there. Let's talk about circles. So that's 2.2. We've talked about circles in our geometry classes. Didn't really talk too much about it in Algebra 2, we just never had the time. So definition. A circle is the set of all points in a plane that are equidistant, form a fixed point called the center. The fixed distance from any point on the circle to the center is called the radius. Okay? So again, circle is the set of all points in a plane that are equidistant from a fixed point called the center. The fixed distance from any point on the circle to the center is called the radius. Okay? Now, let's go further with that. let's say I want to come up with some sort of equation for this circle. Okay, I want to come up with an equation that tells me all the points that are on the circle. Okay, so here's my circle. Did you ever see those competitions? Did you ever, I don't know, it's a competition where they do the circle, the perfect circle, try to do those things. I can't do it with this board. I'd probably just bang my hand off the thing, and that's workman's comp, right? I can't work anymore. My hand can't grip the marker. Okay, so here's my center point, and here is some generic point on the circle. It's kind of weird. I put an open dot there, right? And we'll talk about that at the very end. But that's my center. And my center is going to have some coordinates. The coordinates they usually use with it is H and K. We actually see H and K vertex form. We talked about parabolas. Ugh. Okay, now I want to come up with an equation for the radius. Now why do I want to do that? Because the radius will tell me what all the points that are on this circle, right? Because it has to be equal distance to it. So how do we find that? So how do we find our radius then? Well, it's like the distance formula. I'm going to go a certain distance in the x direction, okay? So that's going to be my x minus h. I'm going to go a certain distance in the y direction, so that's going to be my y minus k. And then I formed another right triangle, so here comes Pythagoras. He's coming back in play. And what I could do is use Pythagorean theorem to come up with an equation for the radius, which will then be the equation of a circle because it tells me every point that's going to be on it. Okay? So far so good. So let's do that. So we have r squared, okay, is equal to x minus h squared plus y minus k squared. So that's just coming from the Pythagorean theorem. And there we go. It's as simple as that. That will tell me all the points that are going to be on this circle. Okay? And let's put some clarifiers underneath it. So this is where h and k are the x and y coordinates of the center, and r the radius of the circle. Okay? Now, notice that in this case, h and k were positive, right? If I drew this over here in the third quadrant, they'd both be negative. So that would change these guys to positives, right? So it's like flip-flopping it. So if you see an equation of a circle with these two being positive, then that means that your center points were negative. They're somewhere over here. So it's always going to be the opposite of what's in here. That's why they say h and k. Now, why did I not include the center point? Well, think about it. If I plug h for here and k for here, I get 0, right? And this says that the radius is 0. Well, that's not what the definition of a circle is. The definition of a circle is points on the circle, not inside of it. So I know one thing in geometry we don't really do a lot of is, go after this guy, because the center point does not work for this. Okay, that's why we have an open dot there. So we just want points that are physically on the circle. Okay. Now I've got the equation, let's work with it. If you remember your geometry classes, we go through circles quickly. We never have enough time in geometry to do everything. Let's talk about the standard form of an equation of a circle. Okay. Yeah, I'll put that, underline that. Given a circle, center at HK with radius r, the standard form of an equation of the circle. And I threw this in here as well. So it's also called the a center radius form. Okay, you could say the word standard form, you might hear center radius form. It's the same thing, but I at least want you to be aware that that also exists in this world. But just from my experience, I usually just hear standard form all the time. Is given by this guy. So what I derived over there, call that standard form, where the radius is greater than 0. Because again, it doesn't make sense for the radius to be 0 because we want a distance from the center for all those points that are equal distant from the center. Okay? Now I want to make a note here, something I added. So note, if r is not r squared, then to find the radius, okay, take the square root of the value. That'll make more sense when we do an example. Okay, so if you had an equation where this wasn't squared and it was just some random number, to figure it out what it was originally, just take the square root of it. Example. Write the standard form of an equation of a circle with center -3, 7 and radius 3. Then graph it. Why not? We do all that work to create something. Let's graph it a little bit. So I'm just going to go ahead and label. So my center is -3, 7, and r is 3. Okay. Let's use, I like this blue. Let's use this blue. Okay. So I want to put it in this format. And we already said that h and k is the x and y coordinates of this guy. So this must be h, this must be k. So now I can plug them directly into there. So it's x minus a -3 squared, and then here would be y minus 7 squared equals 3 squared. Okay? Now simplify when you can. So this will be a positive now, right? And then b squared is none. Okay, so there it is. There's the standard form for that circle with those characteristics. Now let me go back to what I made a note of over there. You see how this is not 3 squared, right? That's not the radius, okay? It's kind of misleading, but remember when I derived it, radius is whatever it is squared. So to get 9, I do what? 3 squared, right? So take the square root of that, boom, now you got the radius. So it's very misleading. That's why I kind of wanted to make sure that I put that underneath it. If it's not written like this, then they simplified it. So you want to find the actual radius, take the square root of that guy. Graphing it. Am I gonna have enough space? Oh, this will be fun. There we go. So there's my center point. And then what I would do to make it easier, I would graph additional points with the radius of 3. So if I go 3 spaces out in this direction, there's a point, 3 spaces up here, 3 spaces across, and 3 spaces down. And then just draw your circle. I missed that point, didn't I? Well, hand-drawn graph. We do the best we can. But that's what I would do. I just use the radius to plot. At least, I think 4 points is good to get a little bit of accuracy there. And then one thing to note, and it's so hard to because we're so used to not doing this a lot, but an open dot in the center, because remember, we're not including the center, so that's just emphasizing that. All right. Let's try another example of this. Write the standard form of an equation of a circle with endpoints of a diameter -2, 4, and 610. Well, that's less information than what we got over here. This one, we had it all. They gave me the center, they gave me the radius, perfect. I plugged it in, got the equation. Okay, this guy over here just gave me a diameter and where does it hit on the circle. That's it. That kind of sucks. What I would do, think about it. If I want to make that equation, I need a center and a radius, right? Those are the two things I have to get. So let's think about a center first. If I had a generic circle like this, here's my diameter. Okay, your diameter always goes through the center. I know what these are. So to find the middle, what would I use? Midpoint formula. Yeah, very good. Does that make sense? If I want to find it? So hey, what we just talked about not too long ago, let's use it. So the midpoint will help me find the center. So we'll do -2 plus 6, take half, and then 4 plus 10, take half. It's one of the main reasons why I just combined the two lessons together, because they do work well. So this will be a 4 divided by 2 is 2. 14 divided by 2 is 7. So there's my center point. I'm going to go ahead and label this as H and K. Do you have to do that every time? No, but I think it just kind of helps since we're just still kind of learning through the process. Alrighty. Now, I got to find the radius, right, of the circle. So how am I going to do that? Well, that's this guy right here, right? So what am I saw your hand up, go ahead.
Yeah, find the distance between the 2 points and then take that in half.
Okay.
Or, well, I guess now that you have the center, you can find the distance between the center and one of the endpoints.
That would be a little bit better, just because like if it came out to be something that doesn't work out nicely, taking half of that might get a little messy. So yeah, I would just take this and any one of the endpoints, right? And the one I chose was the 6 and 10. Not that -2 and 4 is bad, but it's kind of negative. That's scary, right? Negatives are scary. So let's do it. Distance of this guy and the 6 and 10. So we get, I did 2 minus 6 squared, and then 7 minus 10 squared. Okay? So we get this to be -4. Squaring it gives me 16. -3 squared, that gives me 9. And hey, how about that? It comes out nicely. It's almost like I planned it that way when I made this. So we got a radius of 5. Perfect. By the way, if this was still a square root, that's fine. Put the square root in the formula, okay? There's no like rule out there that says you can't. So my equation, I'll write it down here. So it's gonna be x be -2 squared, y minus 7 squared equals my radius squared. So it'd be 5 squared. And then I'm getting, well, I'll put it over here. So we can finish it up by just squaring the 5. So it equals 25. And there we go. Okay. Again, if you get a problem that's written like this, you know that's the radius, you're good to go. But when you're not seeing that exponent, that's when you gotta take the square root to figure out what the radius actually is. All right. We have one more form to go. If you look at the objectives, we have what? General form. So let's talk about general form. And we're gonna need a little help from completing the square to figure out general form. equation of a circle written in the form is called the general form of an equation of a circle, okay? So x squared plus y squared plus ax plus by plus c equals 0. We'll call it the general form. Okay? Now you're probably thinking, where the heck does that come from? we were fine with this. This was fun. This was easy. Well, here's the deal. If I took this guy right here and I expanded, like let's say I multiplied this out, brought the 25 over, I get the general form. That's where it comes from, okay? So it's just us working with the vertex form and what happens when this is expanded. You know, can we work with both types of situations? So let's try an example. So write the equation of the circle in standard form. Then identify the center and radius. Okay? So I'm going to start with the general form, and we're going to create this guy here. Okay, so we're going to go in that direction. Because we already know how to go from that format to general. You just expand it and multiply it out. So nothing too exciting there. Okay, so there it is. There's my equation. I will say, when you see an x squared and y squared, that kind of keys you off into thinking, okay, I'm looking at something circular in nature. Now, how do I make this into that? Well, let me think about something. You see how this right here means this? It's the same guy twice, right? Just condensed. Remember how we called those like perfect squares? They're perfect because they're the same, they come together. I'm gonna need to create that for the x's and y's. And we do that by what's called complete the square, because we did that already in the past. So what I'm gonna do first is group together the x's and the y's and put the constant on the other side. I'm out of space. Sorry about that. I didn't have enough room to move that over. Okay? So what we're going to do is group the x's and y's together and then complete the square. Twice. We're going to do it. Okay? So let's do a little math doodle over here. So remember, when we complete the square, we want to make that perfect square trinomial, which allows us to factor and get stuff like this. So I'm going to take half of 24, and then I'm going to square it, right? So that's going to be 12. 12 squared is 144. So that's going to go here. So therefore, the x's gives me that perfect square trinomial. Now I'm going to do the same thing with the y's. So -4 divided by 2 and squaring it. Okay? So that's -2 squared gives me a +4. So I'm going to put that here. Now because I did that, that's not the same equation anymore. I added stuff to it. So what I have to do to keep things balanced and keep it the same type of equation, I have to add it over the other side. But I have to add both of those values, okay? So like I said, it's like complete the square twice. Now we just gotta factor these and simplify the right-hand side. And we got our equation. So on this side, well, that's just gonna be x plus 12 squared, right? Because 12 and 12 gives me 24, 12 squared gives me 144. And on this side, it would just be y minus 2 squared. -2, -2 gives me -4, -2 squared gives me +4. And on the right-hand side, when we add all those together, that comes out nice. It comes out to 16. Okay. There it is. Hey, that, put it this way. If you had to choose, you want a graph with this, and plug points in? I wouldn't. That is now written in standard form. Now I can use that to graph the circle. So my center is going to be -12 and 2. Remember, it's the opposites of those. And then the radius, see how that's not squared? So I got to take the square root. So my radius is 4 for that guy. Okay? All right. So I got one example left. I got to talk to you about a special case. All right? Can't be a math lesson without special cases. There's always something that makes things just go wrong. That's actually the fun stuff about math. Getting something like this and then making it go wrong. So, going back to standard form. I can spell standard form. There we go. Standard form of an equation, which is this guy. Okay? So going back to this form, when do things not work out well, right? We already mentioned one case. What if the radius was 0, right? Like if we include the center point, the radius is 0, we know that doesn't work out, okay? But what about some other things this could be? So if C is greater than 0, then the graph will be a circle with radius, let me just abbreviate, there you go, where the radius is the square root of C. So that's the normal case, right? This is a positive number, just like we saw down there. We got a circle, we're good to go. Okay, we've also said if the radius is 0, well, then the graph will just be just a single point, which not really exciting. It's just H and K. So the solution set is HK, which again, nothing exciting because we don't want to really worry about the center. We want to find all the points outside that circle. But it does happen at times. Now, the last case, what if it's negative? I think anytime we see negatives, we start panicking. It's like, oh, is that complex numbers again? We wouldn't have to worry about it in this case, because if it is negative, then the solution set is the empty set. Okay, so there's really nothing we can do about it. We don't really have a circle. I'm flirting with the option. In trig, we'll talk about imaginaries and how they work with trig. And I might throw, just not to test you, but I might throw a couple things at you just to show you like how we can still graph circles and imaginary numbers and different things like that. It's a lot of fun. I always enjoyed it. Okay, so let's do one more example. I'm not going to write the instructions out. It's the same instructions as before. So we're going to write this in standard form. Okay. So here it is, our last little example here. Let's write it in standard form. And obviously, after talking about this, something is going to go bump. Okay, something's going to go wrong. So first step, group the x's together. Group the y's together. And start completing the square. Okay. And it's okay, I know these numbers worked out nicely. Is it acceptable to have numbers that are like fractions and stuff? Yeah, that can occur. So half of that, square it, that's 25. Half and square it is 4. So now I'm going to add those to the other side, right? Now, if you pause for a moment just to see, negative 280, 25, and 4. If I were to combine those, is this still going to be negative over here? Yeah. So that's not good. So this is just gonna be y, oh, not y, x plus 5 squared. This will be y minus 2 squared, but this is gonna be negative 251. Yeah, that's not good. You can't have a radius that's negative. Now I'm out of space. I'm gonna write the answer up here. So therefore, the solution set is empty brackets, okay? There's nothing that will satisfy that equation there. So that was a lot, but I think the beginning stuff, we knew how to do distance and midpoint, but that was needed to help us with the circles, okay? Alrighty, I have your practice for tonight. Just going through the same examples there. And after this, I'll pass back your quizzes.